In our previous section, we were doing synthetic division when we knew one of the roots to a polynomial in order to factor it down. And we're going to do the same thing here. We can even do that when one of the roots is imaginary. So here's a polynomial. We called it c of x because its coefficients are actually complex numbers, or at least, well, they all are since real numbers are complex numbers, but 3 of the coefficients actually have I in them as well. So we're given that x equals 9i solves c of x equals 0. It's one of the zeros or the roots of this polynomial. And we want to completely factor the polynomial. Well, I'm going to do synthetic division, just as we did in the previous sections. We've got x equals 9i as the 0, so I put 9i outside to set up the synthetic division. Then we have our coefficients, 1x cubed, 5 minus 9ix squared, 4 minus 45i x, and then negative 36i. And this actually, it looks kind of daunting, but look how nicely it works out. We know we're going to get a remainder of 0 if the problem's correct. We drop down the 1, and then we multiply by 9i, and we get 9i. When we add it, we see that the imaginary part cancels. We have 5 minus 9i plus 9i would just be 5. And then we have 5 times 9i is 45. Once again, the imaginary cancels. 4 minus 45i plus 45 will give me 4. And then I multiply 9i times 4, and I get exactly 36i, and I add those together, we get a remainder of 0. So we do have a remainder of 0, which is showing that c of 9i is 0, and we have our quotient there. Our quotient is x squared plus 5x plus 4. So we have factored our polynomial into the linear term with the complex root, x minus 9i, times this quadratic with real coefficients, x squared plus 5x plus 4. And that's quadratic, and we can factor it one more step. 4 times 1 would be 4, and 4 plus 1 is 5, so we can factor that into x minus 9i times x plus 4 times x plus 1. The question just said to factor, but if we wanted the zeros, they would be 9i, negative 4, and negative 1 if we set each piece equal to 0. Okay, what's up next? So we're talking about zeros, and we have the intermediate value theorem, which is a consequence of what we call continuity. If you take any function, including polynomials, that are continuous, meaning you can draw them without lifting your pencil, if you think about them that way kind of informally, that there's no breaks in the graph. You can't cross from positive to negative y values without crossing the axis is basically what the intermediate value theorem says. It's actually more general than that. The intermediate value theorem says that your function, if it's continuous, will take on every value between f of a and f of b, but we usually use it in this setting where you have opposite signs. So if I have two x values, a and b, and the two function values there have opposite sign, one of them's negative, one's positive, in either direction there, polynomials are continuous. If I'm going to go from positive to negative or negative to positive, I have to cross the x-axis. So if we know we have a sign change, then we have to have a root, a 0 in between. It's pretty easy to verify, like in an example like this, if I want to show that p of x equals x to the third minus 2x minus 4 has at least one 0 in the interval from 1 to 3. And now keep in mind, it could have more than one, but the continuity tells me it has at least one. Okay? I just have to show a sign change, which I already have on the screen here. I didn't animate this one. I just have to plug in the two endpoints, 1 and 3, and show that we get opposite signs. So if you take x to the third minus 2x minus 4 and you plug 1 in, you wind up getting negative 5 if you evaluate that. If you plug 3 in, you get positive 17. I think I made the extra note. Yeah, since p is a polynomial, it's continuous, and p of 1 is negative and p of 3 is positive, then p has at least one 0 in the interval there by the intermediate value theorem. So we had the linear factorization theorem that said if I'm willing to go into complex numbers, I can factor every polynomial into a constant times a product of linear terms. This corollary, which is just something that follows quickly from a theorem, the corollary to the linear factorization theorem says that if I don't want to go into complex numbers, I can factor into linear and irreducible quadratics. Okay? The quadratics could have the imaginary roots, but if we're only willing to use real numbers, sometimes we have to stop at quadratics. Like the x squared plus 25 in a previous example, that can't be factored without using imaginary numbers. Another theorem, the complex conjugate theorem. Now earlier I did a polynomial and 9i was one of the roots, but the coefficients were complex, and negative 9i was not one of the roots, but the coefficients were complex. If you have real coefficients a plus bi will only be one of the solutions, one of the zeros, if a minus bi is one of the zeros. For real polynomials with real coefficients, any complex answers always come in conjugate pairs. That's because they're coming out of the quadratic formula, which has the plus or minus square root part. So they're always going to come in the plus or minus pairs. Okay? And when you multiply them out, you wouldn't get real coefficients if you didn't include the plus or minus parts. I'm going to use that on this example. Find a polynomial with integer coefficients and roots x equals 1 and x equals 1 plus square root of 2i. Now I didn't say in the problem that 1 minus square root of 2i is one of the roots, but it has to be, okay, because we want integer coefficients, and integers are real numbers. So my polynomial that I can use, I could multiply by anything that I wanted, any constant that I wanted, but the simplest thing is just to do 1 times x minus 1 times x minus my complex root 1 plus square root of 2i, and I've put that in parentheses to be really careful. We're subtracting the whole thing. And then I have to include this last term or I will not get real coefficients. I have x minus the conjugate of that complex 1 where I change the plus to a minus, 1 minus square root of 2i. And now this is going to get a little messy to multiply it out, but everything will eventually work out nice here. First thing I'm going to do is run the negatives through. So I have x minus 1 times x minus 1 minus square root of 2i if I distribute the negative, and then x minus 1 plus square root of 2i when I distribute the negative. Next, I'm going to multiply the two that had the complex conjugates in there together, because even though it's a big mess, it's going to simplify tremendously when we look at it. So we have x minus 1, and now this is a little tedious, but remember when you multiply polynomials like this, you do every term times every term. So let's see, I'm going to do x times all three terms. That would give me x squared minus x plus x times square root of 2i. Okay, so these first three terms are x times this x minus 1 plus square root of 2i. And then I'm going to do negative 1 times all of those. I'll get negative x plus 1 minus square root of 2i. And then finally, we do negative square root of 2i times all those. You get negative square root of 2i times x, or negative x square root of 2i. And then negative square root of 2i times negative 1 will be plus square root of 2i. And then finally on the end, we have a negative, and square root of 2 times square root of 2 would give me 4. So I get negative 4. Sorry, square root of 2 times square root of 2 would give me 2. So we have negative 2i squared. The I squared changes the sign to plus 2. Okay. So 3 by 3 actually gives me 9 terms. It takes quite a bit to multiply it out, but I just do x times all 3, negative 1 times all 3, negative square root of 2i times all 3. And then we can look and see what happened here. We get our x minus 1, and this actually is just x squared minus 2x plus 3. Let's see, we got our x squared. We've got a negative x and a negative x. That's negative 2x. We have x squared of 2i. Somewhere over here we have a minus x squared of 2i, so those cancel out. We've got a plus 1 and a plus 2 is where the 3 comes from, and then we have a negative square root of 2i plus square root of 2i. Those cancel out. So all of the terms with the i's cancel out. That's what happens by including the conjugate in here as one of the roots. And then we multiply those out. So I do x times all three terms and 1 times all three terms. So we get x times x squared is x to the third, x times negative 2x is negative 2x squared, and then plus 3x. And then minus 1 times all those terms will be minus x squared plus 2x. That should be a minus 3 on the end. That's a typo. Negative 1 times 3 would be a minus 3.